Hi, everybody here. I'm pleased to introduce myself. I am Dr. Aymen. I am a researcher in the University of Mosul in Iraq. This research was carried out at the Institute of Material Science and Engineering in Technical University of Gloucester in Germany, at the request of Pillar and Blowers Compressors Company in Germany, also to selection the suitable materials impeller pumps applications, taking into account the economic cost, provided that this does not affect the performance. We were provided by the company with these two alloys, the titanium with this composition elements, titanium 6 aluminum 2 niobium 1 tantalum 1 molybdenum, and the duplex stainless steel for the comparison in their resistance to the corrosion under environmental condition specified by the company, namely acidity, temperature, and different concentrations of chloride with the addition of magnesium solution in some cases. Now, choosing suitable materials reduces the risk of the corrosion and failures of the pump. So still the corrosion is the main problem leading to pumps rapid failure, especially in harsh environments. Therefore, choosing the materials is a crucial factor to the success of any pumps applications, and their initial cost is usually the first consideration. And the other factors to be considered in selecting these materials for weighted pumps parts are expected pump life, continuous duty, the pumping of the hazardous or toxic liquids, conditions of liquid and pump sections, energy level, and the conditions of surface. Now, why have the duplex stainless steel and the titanium alloys have been selected in this study? We selected the duplex stainless steel as the superior alloys in the stainless steel group regards the corrosion resistance. So previous studies indicates that duplex steel is superior to the other types of stainless steel regards the corrosion resistance, because it has elements that contribute to the stability of oxide film. Compared to the austenitic stainless steel, duplex stainless steel differ mainly in their chromium, nickel, and molybdenum content. Chromium is a ferrite former. At higher chromium percent or content, more nickel is necessary to form austenitic structure or duplex structure. This table indicates that the presence of high percentage of chromium, about 22%, that is responsible for the formation of the chromium oxide, which protects the base alloys, and molybdenum contributes to the stability of the oxide film significantly, and the addition of nickel accelerated the cathodic reactions, while the addition of molybdenum contributes or retards the anodic process. The more content of nitrogen in duplex compared with conventional stainless steel contributes significantly to increasing the chloride corrosion resistance. Now, the pair of the duplex alloy of the titanium alloy group was titanium 6 aluminum 2 niobium 1 tantalum 1 molybdenum alloy, and this alloy contains the elements tantalum and molybdenum, which contributes to the stability of oxide significantly. Therefore, these two alloys were chosen to compare them in terms of corrosion resistance. Now, the motivation of this study the environment in which this alloy operates in many industrial applications, such as fluctuations in concentrations, differences in pH, and relatively high temperatures, call us to test this material in different environmental variables. So this is a study aims to cover several complicated environmental variables, including the effect of chloride concentration, pH, and temperature on duplex stainless steel and titanium alloys to give us more accurate precision about the differentiation between these two alloys and their use in the pump impeller applications. Now, at first, we investigated the effect of sodium chloride concentration on the corrosion resistance of both alloy. So the solution was prepared in 3 concentrations, 5%, 10, and 20% of sodium chloride. And in this test, the temperature and pH were set at 90 degrees centigrade and pH 7, respectively. Now we see in the potential dynamic polarization curve, and the data in this table deduced from this curve indicated that the increase in the chloride concentration lead to increase significantly in the corrosion current density and the corrosion rate, as we show here that the current or the corrosion current density increased from 2.13 to about 8 microampere per centimeter square, and the corrosion rate increased from about 0.712 to 1.9 millimeter per year when the chloride concentration increased from 5 to 20%. And further investigation was also done by using the the impedance spectroscopy, and this scanning impedance spectroscopy show the Nyquist plots obtained in the solution in the 3 concentration of chloride. The Nyquist plot, so the Nyquist plot is a plot of real impedance versus imaginary impedance. And the bigger the radii of arc are, the stronger the electrochemical impedance will be. So this test supports the results obtained in the potential dynamic polarization. So we will note that a significant decrease in the electrochemical impedance of duplex stainless steel with the increase in the concentration of sodium chloride. Also, the SEM, or the scanning electron microscope of duplex stainless steel, show that or support our results in the electrochemical test. And we note that the pitting or the corrosion pittings increase in size and the number with increasing with the chloride concentration, as we show here, that the pittings increase significantly in the size and the number also. Now, for the titanium, here we note that there is no significant effect on the corrosion behavior of the titanium after this is test. So we note that there is slightly increase in the corrosion current density and corrosion rate. So the corrosion current density increased from 2.7 to 2.9 microampere per centimeter square, and the corrosion rate increased from 0.6 to 0.65 millimeter per year when the chloride concentration increased from 5 to 20. Also, the scanning electron microscope for the titanium alloy after this test show that there is no significant effect and no traces, no defect on the surface of this alloy after this is test. Some traces of the corrosion after electrochemical test at the 20%. Now, we can explain this as a result. We note that the increase in the chloride concentration or the chloride ions has significant effect on the corrosion behavior of duplex stainless steel. And this is due to the chloride ions slowly penetrating into the surface, at which the protective film is destroyed and the steel begins to corrode. And the chloride corrosion tends to evenly pit the entire surface area of the specimen with the shallow, irregular shaped pits. Chloride penetration is metal due to the presence of different mechanisms, mainly diffusion and capillary absorption. The effect of the increasing the concentrations of sodium chloride on the corrosion resistance of titanium alloy was slight compared to that of the duplex stainless steel, which is mainly due to the fact that the titanium alloy contained molybdenum and tantalum elements, make the passive film more stable. In addition, it is reported that the aluminum could be oxidized and form a compact aluminum oxide layers on the top of the passive film, inhibiting the dissolution of the oxide film. Now we go to the effect, to the second parameters, the effect of the pH or the acidity on the corrosion resistance on the duplex stainless steel. It was reported in a previous study that the corrosion in the magnesium chloride solution is higher than the sodium chloride due to the relatively high viscosity compared to the sodium chloride solution. And because of multiple operating environments and to cover the maximum possible of the influencing surrounding environment factors, it is necessary to study the effect of mixture of these two solutions on the corrosion performance under relatively high temperatures and multiple pH values. So the samples were tested in 10% sodium chloride solution with the 3% magnesium chloride added at pH 7, 4, and 2 at 90 degrees centigrade. So this figure represents the potential dynamic polarization, and the data here in this table represent the data deduced from this curve, and we note that the decrease in the pH leads significantly or extremely in increasing the corrosion current density and the corrosion rate, as we show here, that the corrosion current density increased from 4.3 when the pH was 7, increased to about 27 microampere per centimeter square when the pH became 2. And also the corrosion rate was increased from 1.2 to about 8.2 millimeter per year when the pH decreasing from 7 to 2 respectively. So this extremely increases the corrosion current density, and the corrosion rate call us to more investigation by the electroimpedance spectroscopy. And also from this test, we show that there is a significant decrease in the impedance when the decreasing in the pH from 7 to the pH 2. So the impedance for the sample tested in the pH 7 was about 4.5 kilo ohm and became about 1.4 kilo ohm when the pH decreasing to 2. This SEM observation support the results obtained in the electrochemical test, and we show that the surface at the pH 2 entirely pitting, and there is significantly increase in the size of pitting and the number of pitting when decreasing in the pH. We note that the pitting corrosion was very small and very little in the pH 7, and they can increase gradually with the pH decrease to 4, and became very big and very large when the pH decreased to 2. The same also applies for the titanium alloys. We show that a significant also increase in the corrosion current density from about 3.06 to 4.24 microampere per centimeter square. And the corrosion rate also increased from 0.69 to 0.95 millimeter per year. Also, the electroimpedance spectroscopy indicates the same results, where the impedance decreased from about 23 kilo ohm for the sample tested at pH 7, decreases to about 8 kilo ohm for the sample tested at pH 2. The scanning electron microscope indicates that the pH 7, or the sample tested in the pH 7 and pH 4, there is no defects, there is no pits, but in contrast at the pH 2 appeared the crevice corrosion at the surface of the titanium alloys after decreasing the pH to this is value. Now we can explain this is results. The addition of magnesium chloride played an important factor in increasing the corrosion rates of two alloys, and this is consistent with what was stated in the previous studies, where it is found that the increase of the corrosion rate due to the magnesium chloride solution having a higher viscosity and stronger hydrophilicity than the sodium chloride solution, which makes the magnesium chloride molecules stick and crystallize on the surface and react with the metal quickly. Generally, corrosion resistance of stainless steel is achieved by dissolving of sufficient amount of chromium in iron to produce the coherent, adherent, insulating, and regenerating chromium oxide protective film on the surface. And this passive film of chromium oxide formed in the air at room temperatures is only about 1 to 2 nanometer. And the pitting corrosion is the result of the local destruction of the passive film and subsequent corrosion of the steel underneath this layer. The duplex stainless steel micrograph in this figure, or in the for the scanning electron microscope, indicates that the pit initiation frequency increase with the pH reduction. And this is because low pH solutions accelerate the corrosion by providing hydrogen ions, and the hydrogen attacked and damaged the surface of the steel and increase the corrosion rate. The pitting formation is influenced by many factors, such as the presence of a highly corrosive film containing a chloride compounds, because negatively charged chloride ions migrate into the pit to balance the positively charged metal ions. And here in the scanning electron microscope for this titanium alloy, after electrochemical test, the appearing crevice on the surface at pH 2 was due to the dissolved oxide film of titanium. And it is reported that the strong reducing acidity dissolves the titanium oxide film radially, and the alloy is activate and prone to attack. If the acidity is strong enough, titanium hydride film is formed on the surface of titanium once the oxide film has been dissolved. So the titanium film is equally protective, but it does not develop spontaneously like the rutile oxide. Now we go to the third parameters, the effect of temperature on the corrosion resistance of duplex stainless steel. The electrochemical corrosion test shown in this figure and the data in this table indicates that the corrosion rate and corrosion current density at 54 degrees centigrade are much lower compared to the sample tested in the temperature 90 degrees centigrade. So we note that the corrosion current density was about 1.5 at the temperature 54 and became 4.34 at the temperature 90, and the same for the corrosion rate. We note that the significantly increase in the corrosion rate from 4.41 to 1.23 millimeter per year when the temperature increasing from 54 to 90 degrees centigrade. Also, the electroimpedance spectroscopy was done to study the effect or investigated the effect of the increasing in temperature, and we show that the increasing in the temperature leads to decrease the impedance for the samples or duplex stainless steel alloys. We show that the samples tested in the 54 degree was about 8.9 kilo ohm and decreased to about 3.9 kilo ohm when the temperature increased to 90 degrees centigrade. Also, the optical or the scanning electron microscope show that there is a few pits and the very small pitting in the surface of the sample tested at 54 degrees centigrade, and this is gradually increased in size and the number of the pitting with increasing the temperature and became large at the 90 degrees centigrade, as we show here, and this is third picture. Also, the effect of temperature on the corrosion resistance of titanium was done by using the potential dynamic polarization, and we show that the same results, but this effect was slightly compared with the duplex stainless steel. So we note that the increase in the corrosion current density from 0.4 to 3.06 and the corrosion rate from 0.107 to 0.69 millimeter per year when increasing the temperature from 54 to 90 degrees centigrade. And the scanning electron microscope after this is electrochemical test showed that the clean surface after this is corrosion test and no defects, no traces of the corrosion. So the results deduced, we can explain these results. The result deduced from the electrochemical experiments and the metallographic observation confirm that the temperature plays a crucial role in the influencing the corrosion resistance. And the high corrosion rate of duplex stainless steel may be related to the high dissolution and instability of oxide film at 90 degrees centigrade. And this is in a good agreement with the previous studies. Finally, this is two alloys, now we go to this is two tables. Summarize the results obtained in the electrochemical corrosion test under the conditions or conditions, and prove that the titanium has the superiority of the duplex stainless steel to resist the corrosion and the pitting. And this is due to the several factors, the most important of which are the elements that make up the alloy, such as tantalum, molybdenum, and aluminum, which make the oxide film more stable. In addition, the reason for this superiority of the titanium alloy over steel or over duplex stainless steel in regards to the corrosion resistance is mainly due to the fact that the main element in the titanium alloy is the titanium element, which forms the titanium oxide. This is titanium oxide regards the pair of the chromium oxide in protecting the base alloy from the corrosion. But at the same time, duplex stainless steel can be the ideal alternative to the titanium alloys because of its excellent resistance to the corrosion compared to the conventional stainless steel, and it is lower cost compared to the titanium alloys. Now, finally, the main conclusion drawn from this study are summarized as follows. Number one, the titanium alloy has superiority over duplex stainless steel alloys regarding the corrosion resistance at all conditions. Number two, the lead pH reduction to significantly increase the current density and corrosion rate of both alloys. Number three, the change in the chloride concentration and temperature had more substantial impact on the corrosion behavior of duplex stainless steel than on titanium alloys. Number four, the pitting corrosion was formed on duplex stainless steel samples in all conditions, while the crevice corrosion was developed on the titanium samples with the presence of magnesium chlorides at pH 2 and the temperature 90 degrees centigrade. Number five, the magnesium chloride ions in low acidity solution appear to interact with the repassivation process at the surface of these alloys and influence resulting surface topography. Thank you very much for your attention.